divides relation. If a, b, c are integers such that a divides b and a divides c, then a divides mb plus nc. Whenever m and n are integers, proof from previous theorem, part 3, a divides b and a divides b. It follows that a divides mb and a divides nc. Again, from previous theorem, part 2, that is a divides b and a divides c, then a divides b plus c. It follows that a divides mb plus nc. The division algorithm says that let a be an integer and d a positive integer, then there are unique integers a, q and r with with r greater equal to 0 and less than d, such that a is equal to dq plus r. And it is really just a theorem, not an algorithm, only called an algorithm for historical reason. Q is called the quotient, r is called the remainder, d is called the divisor, and a is called the dividend. Here q is called the quotient, r is called the remainder, d is called the divisor, and a is called the dividend. What are the quotient and remainder when 101 is divided by 11? When 101 is divided by 11, the quotient will be 9 and the remainder will be 2. Because we write it is in the form q equals 9, and that is equal to 101 divides 11, r is equal to 2, 101 mod 11. If a equals 7 and d equals 3, then q equals 2 and r is equal to 1. Since 7 is equal to 2 into 3 plus 1. This is dividend is equal to divisor into quotient plus remainder. If a equals minus 7 and d equals 3, then q equals minus 3 and r is equal to 2. Since minus 7 is equal to minus 3 into 3 plus 2. So, given positive a and positive d, in order to get r, we repeatedly subtract d from a as many times as needed. So what remains, r is less than d. Given negative a and positive d, in order to get r, we repeatedly add d to a as many times as needed, so that what remains r is positive or 0 and less than d. This is the division algorithm. Let a be an integer and d is a positive integer, then there are unique integers q and r with r greater equal to 0 less than d, such that a is equal to dq plus r. This is dividend, this is divisor, this is quotient, and this is remainder. Prove that we will use the well ordering property directly, that states that every set of non-negative integers has at a least element. We want to show that existence of q and r with the property that a is equal to dq plus r and r is greater equal to 0 less than d. Consider the set of non-negative numbers and of the form a minus dq, where q is an integer. So can this set be empty? Note, this set is non-empty since q can be a negative integer with large absolute value. By the well ordering property, S has at least element, r is equal to a minus dq0. R is non-negative, also r is less than d. Otherwise, if r is greater than or equal to d, there would be a small non-negative elements in S, namely a minus d into q naught plus 1 greater than or equal to 0. But that a minus d into q naught plus 1, which is smaller than a minus dq naught, is an element of S contradicting. There a minus dq naught was the smallest element of S, so it cannot be the case that r is greater than or equal to d, proving the existence of r is greater than or equal to 0 less than d and q.